Solving congruences, section 4.4. A linear congruence is a congruence of the form AX is equivalent to B mod M, where A and B are both positive integers and X is a variable. So let's say we want to find a solution. What variable makes the following true, where 2x would be equivalent to 7 in a modulo 9 world, right? So we're only looking at the numbers 0 through 8, because those are the numbers that exist mod 9. So one way to do this is just brute force. If the only possible numbers for my variable are 0 through 8, that's only 9 things to check. So 2 times 0, that's equivalent to 0, right? 0 mod 9 is 0, so not too difficult there. Same for 2 times 1. 2 times 1 is 2. Mod 9 still gives me 2. 4 mod 9 is still 4. 6 mod 9 is still 6. It's not until you get to 2 times 5 that something interesting happens, right? 2 times 5 is 10. Mod 9 is 1. So 2 times 5 is equivalent to 1 mod 9. We finish this out to try 6, try 7, try 8. And then we just look through that. Let's say, okay, are any of these equivalent to 7 mod 9? Sure enough, 8. So 8 is the only solution in mod 9. That is 0 through 8. Recall this theorem, though. We're going to be utilizing the top one there, the addition. So this is from a previous presentation. We knew that if we had A was equivalent to B mod M and C was equivalent to D mod M, then you would get the fact that A plus C would be equivalent to B plus D. We're going to combine this with the fact that we know that 9 mod 9 is 0. We know that 8 is a solution, but we can find an infinite number of solutions by adding multiples of 9. We can go the other way and subtract multiples of 9. So here we see there's an infinite number of possible solutions to this statement. Find a solution. What if we want to find all solutions to 3x is equivalent to 2 modulo 6? Again, we'll try brute force here. There's even less to check. Note here, I'm going to try 0 and 6 again, even though they are equivalent in a mod 6 world. And that's because I want to show you that this pattern continues, right? This is, if you went further into some modern algebra stuff, this is called the orbit of an integer in a modulo world. But what we see here is a pattern. 0, 3, 0, 3, 0, 3. Multiples of 3 are locked in this equivalence pattern. And so there's no solution. So for this course and moving forward, in particular, we're going to be interested in restricting our attention to solving congruences where AX is equivalent to B mod M, where the GCD of the multiple A and the number we're modding by M is 1. So A and M need to be relatively prime. M is going to be positive. The nice thing about this is that such systems will have a unique solution in a mod M world, that is, in the set of integers from 0 to M minus 1. So let's return to this. Let's solve 2x equivalent to 7 mod 9. And how can we do this without brute force? Well, let's consider a slightly different question. How would you solve 2x equals 7? Well, for 2x equals 7, probably what came to mind immediately was, we'll divide both sides by 2. But remember that we're trying to relate this technique back to our mod 9 stuff. And in a mod 9 world, right, where we're moduloing by 9, there is no division. So let's tweak the idea a little bit. The same thing, we can get the same result as divide by 2 if we think of this as multiplying by a half. In this case, we get that x is equal to 7 over 2. And this is because 1/2 is the multiplicative inverse of 2. That is, that when you take a half and 2 and multiply them, you get 1. Well, now we're in business. We don't actually have division, but we might have a multiplicative inverse. So if a is an integer and m is a positive integer, there exists a bar, we'll go ahead and call it the inverse, if there exists one of these, where you multiply a bar and a, and that's equivalent to 1 mod m, then we call a bar an inverse of a modulo m. Importantly, they're an inverse. So let's go back and look at all the results of 2, because that's what we're multiplying by. So if we want to find an inverse of 2 in mod 9, we are looking for a number that when we multiply by 2, it's equivalent to 1. Sure enough, we find it in 5 right there. So therefore, 5 is an inverse of 2 modulo 9. It's maybe not the only one, but is an inverse. So in a modulo 9 world, 5 times 2 is 1. Importantly, if we meet the conditions we were talking about before, that is where a and m are integers, m is greater than 1, and a and m are relatively prime, that is their GCD is 1, there is a unique inverse of a modulo m in the set 0 to m minus 1. We tend to call that the inverse. So how are we going to go? Let's go all the way back here. How are we going to solve? This all started with us trying to solve 2x is equivalent to 7 mod 9. Well, now we have the multiplicative inverse. We can multiply both sides by 5. Now, on the left-hand side here, that's going to look kind of odd to us at first, right? 5 times 2 is 1. If the numbers are really large, you're going to be tempted to do this and actually take the mod. But the whole power here is that we now know that 5 and 2 are inverses. So when you multiply them, what does it mean to be an inverse? They're multiplicative inverses. You multiply them, you get 1. On the right-hand side there, 5 times 7 is 35. Modulo 9, that gives me a remainder of 8. So x will be equivalent to 8 modulo 9. So that means we can use inverses to quickly solve these, but now we have a whole other question in front of us. How are we going to find these inverses? So how could I have found that 2 had inverse 5 in modulo 9? And the answer is actually going to come from a pretty interesting place. Let's apply the division algorithm here. So we're going to take 9 and divide it by 2. The result is written here, 9 is equal to 2 times 4 plus 1. The nice thing here is that the plus 1, because a simple rearrangement here will give us 1 can be written as 9 minus 4 times 2. So 1 copy of 9 and negative 4 copies of 2 is equal to 1. This negative 4 then is an inverse of 2 modulo 9. We'll go more in depth in this in a minute, but try and think about this conceptually for a second. We're on a clock that has 9 hours on it. 1 times 9 says turn the clock 1 full rotation. That's not going to change it anywhere. But now I do -4 rotations, so counterclockwise, 4 sets of 2 hours. And this is stating that it will be pointing at 1, right? It's equal to 1. So -4 is an inverse of 2 modulo 9. That's not in that pocket from 0 to 8 in this case, but that's okay. We can add or subtract 9s to get there. So let's add 9 to -4. We get 5, right? So 5 is an inverse of 2 modulo 9. Go back to this part in the presentation as much as you need because we're going to expand upon this. The trick is to get it so that we can write an equation equal to 1. Let's find the inverse of 10 modulo 33. Going to apply the Euclidean algorithm to this. And on that second step right there, I get 10 equals 3 times 3 plus 1. Aha, got it. So that line will allow me to write something that is equal to 1. That is 1 times 10 plus -3 times 3. The important thing here is that I'm talking about tens and threes. Right? So if we were following the Euclidean algorithm strictly, that top line says the GCD of 33 and 10 is equal to the GCD of 10 and 3. So the numbers in question, the ones to pay attention to, are the 10s and the 3s. So what you're going to hear me refer to a lot, I'm going to go ahead and get rid of that bottom equation. And I just want to be clear when I say this, what I'm trying to convey. I'm going to be saying linear combinations of blank and blank. So this equation, 1 times 10 plus -3 times 3, is a linear combination of 10s and 3s. That is, it's so many multiples of 10 plus so many multiples of 3. Because we don't get me wrong, we are going to be worried about the A and the B, but the important thing is writing it in this form. Right, so on this line, because we're talking about the GCD of 10 and 3, we're writing 1, right? It's 1 equals, and then a linear combination of 10s and 3s. Because this next step is going to get hard to follow. So I'm going to do my best here to illustrate it. Go back, write all this down, and see if you can follow it. Right? This next equation gives me a way, right? The first equation there had remainder 3. So what are we going to do with it? Well, it gives me a formula to write 3 as a linear combination of 33s and 10s. So I am going to replace this 3 with the formula that is a linear combination of 33s and 10s. Let me clean this up just a little. Now, why do that? Well, the first line there was a combination of 10s and 3s, linear combination. Now, I found a way to rewrite 1 as a combination of 10s and 33s. Right? Distribute your -3, collect your factors. So try and think of 10 and 33 as your variables, right? If you're having a hard time following this, on this line right here, replace 10 with x and replace 33 with y, and you'll see how I'm getting these coefficients. So we get this, the second line provides -3 copies of 33 plus 10 times 10. Well, now this is just what we're after. Because I've now written 1 as a linear combination of 33s and 10s. In particular, -3 33s and 10 10s. Well, we're after finding that inverse. I'm going to work through this once, and then hopefully after you see it, we'll just be able to move more quickly through this part of it. A plus B mod M is equal to modding A by M, modding B by M, adding those, and then modding by M the result. So I'm going to mod both sides of this equation by 33. 1 mod 33, sorry, typo there, I have just mod 3. 1 mod 33 is easy. That's just 1. But now, instead of mod 33, the result of -33 and 10 times 10, let me take the mod of both parts. Now I'm doing this because -3 times 33 is a multiple of 33. So what's the division with the remainder? 0. Which just leaves 10 times 10 mod 33, then mod 33 again. Well, after you've already found the remainder of division by 33, finding the remainder with division by 33 isn't going to change anything. So we can see that the left-hand side is, again, typo, 1 mod 33, 1, is equal to 10 times 10 mod 33. In other words, we've found our inverse. 10 is its own inverse if we are modulo 33. Let's try another. Let's find the inverse of 34 modulo 89. Euclidean algorithm. Now, instead of writing GCD on each one, this is the technique I use. I like to underline. Each line, what am I trying to write a linear combination of? So on the first one, I want to be able to write 1 as a linear combination of 89s and 34s. Sorry, I shouldn't say first one, the top line there, right? The final equation I get should be a linear combination of 89s and 34s. The second line from the top will provide me a way to write 1 as a linear combination of 34s and 21s. Complete my underlining for the rest. Now, that last equation there gives me my start. I can write 1 as a linear combination of 3s and 2s. I'm going to work my way all the way back up this chain, because going from that bottom line, where I've written it as a combination of 3s and 2s, move up a level, I'm going to, instead of writing it with 3s and 2s, I'm going to use that to replace the 2 and write it as a combination of 5s and 3s. So using the equation, right, subtract that 1 copy of 3 to the left-hand side there. That tells me 2 is equal to 5 plus -1 copy of 3. -1 times 3. Clean it up, and this is my linear combination of 5s and 3s. Importantly, you can tell this process is long. Anytime you think you've made a mistake, stop and do an arithmetic check. What is -5 plus 6? It's 1. Every line should result in 1. Move up a level, right? 3 can be written as a combination of 8s and 5s. So 1 can be written as a combination of 8s and 5s. Try to track. One reason why we want to track with underlines here is that you'll notice that even though I tried to get rid of 2 at the very beginning, right, I didn't want to write it as a combination of 2s. 2 has shown up both times as a multiple, right? But the important thing, and that's why I read it this way, is I had 2 3s and now I have 2 8s. I'm not reading as 8 2s. So I've found a way, right? Don't concern yourself with how many I have. I've found a way to construct 1 using 2 8s and negative 3 5s, right? As a linear combination of 8s and 5s. Continue on my way up. And I can see that 1 can be written as 13 times 89 plus negative 34 times 34. Got it. I now have 1 written as a linear combination of 89s and 34s. Therefore, negative 34 is an inverse. So we want to find 1 in that modulo 89 world, right, from 0 to 88. So we're going to add an 89 to that, right? Turn the clock 1 rotation, and we get 55. And we tend to call that the inverse.